super excited today. My name is Russ Sorrells. I'm with CapEx Sales, and CapEx Sales, we've been around since 19, yeah, since 2004, actually, late 2004. So we've been here in the Carolinas for many years. We've been blessed to have the opportunity to serve many customers here in the Carolinas. So we've been working with Cincinnati Test Systems all of those years. I personally started working with Cincinnati Test Systems all the way back in about 1994, 95 timeframe, which is about the time that Gordon Spleet joined Cincinnati Test Systems. So was it 94 when you joined, Gordon?
95. So you and I
95.
became, yeah, you were a customer about the same time I started. It was pretty interesting.
Yeah, for sure. So here we are, however many years later, we're hosting a conversation here, this webinar, where we're going to be talking about the fundamentals of leak testing. So my role during this conversation is just going to be to facilitate some examples, ask questions. We want to encourage the audience to please ask questions so that we can answer your questions. We know that through examples, we've done this hundreds of times. We know that it's the examples that is really meaningful and helps us all learn better. So that is um, that is what we know. So again, my name is Russ Sorrells, and my role is to just help facilitate this dialogue about leak testing, and my role here at CapEx is to support Chris Mullins and Matt Matheny, who are out there in the field every day um, supporting our customers. So that's kind of the role I play in facilitating some of these conversations. So you may have received an email or two from me over the years. So we are grateful for the opportunity to serve. Now, as I mentioned, Gordon Spleet has been with Cincinnati Test Systems since 1995. He's had many different roles throughout his time at Cincinnati Test Systems. His current role is focused on supporting our you can speak to this better than I, but
Yeah.
supporting our marketing in education and getting out there into the market, sharing what we know with our customers so that we can grow the knowledge. We know that a smart customer, an educated customer, is the best customer to have. So that's what Gordon is trying to facilitate in his role. Gordon, what did I miss there? I mean, there's a
Oh,
lot there.
yeah. My past background is quoting, applications engineering, account management, product management, product group management. So I was the marketing director for CTS, and as we grew, those marketing requirements grew as well. So we've got a marketing team with a corporate director doing all the marketing, and now I am supporting CTS marketing, but also global product management. So uh, instrumentation, turnkey test systems, helping our sales reps uh, present our products to our customers so that we can supply the best product, best instrument for the application. So a lot of that's application support as well.
Absolutely. Are there any slides? I think the first couple of slides show exactly what we do to kind of
Yeah.
educate or enlighten any customers that are not familiar with our breadth of capabilities.
Yeah, so a little bit about what we'll talk about today. Correlation of leak rate. Well, first I'll present CTS, who we are today, and then we'll go through correlation of leak rate to airflow rates, what IP67 really means related to that, leak test fundamentals that we'll be discussing, the ideal gas law, factors affecting leak rate variation that affects your test results. The variation is temperature, debris, calibration, resolution. And then we'll go into details about leak testing technologies, the sensitivity ranges of all those technologies, and a really good overview of pressure technologies that includes pressure decay, differential pressure decay, and mass flow.
Excellent.
So with Cincinnati Test Systems, we, like Russ was saying, we are in the Cincinnati area. We were established 1981, and we are now located in Harrison, Ohio, with 80,000 square feet of manufacturing and office space. Our sales are direct. Well, our support is direct sales, service, application engineers throughout North America, in Germany, the UK, India, China, and Korea. So we're just not located in Cincinnati anymore. We're a worldwide organization,
Been fun
and
to
we
watch it
have,
grow.
oh yeah, it has been too. And we have sales, service, representation throughout North America. Groups like CapEx absolutely support all your needs for Cincinnati Test Systems in your area. And then we also have support in Brazil, Argentina, Ireland, Israel, Southeast Asia, Australia, and New Zealand. And we are the leading solutions provider of leak test instruments and turnkey systems in North America by supplying over 5,000 instruments and turnkey systems annually. So that's been a lot of our growth. And this is a real quick slide that shows that Cincinnati Test Systems also is involved with Symmetric, a data solutions supplier who was also a leak test company out of Canada. We're also associated with Innomatic, a German leak test company and turnkey systems provider in Europe. And we've got new offices in India, in China, and Korea that support all of those businesses as well. The industries that we support, well, Russ, you and I grew up in the automotive and transportation industry, which really has grown our business into powertrain, electric vehicles, the appliances. Uh, there's a lot happening in HVAC industry. Matt Matheny's really involved in that from your group. And we also have been supporting consumer electronics and the medical industry very heavily with other industrial applications.
Yeah, it is amazing how it has transitioned over time. It's just interesting to go back and think about the trends. So if you remember, Gordon, which I'm sure you do, we had the airbag industry,
Oh yeah.
and that that exploded the business. That was kind of a level up, and then fuel systems with the Lev 1, Lev 2 requirements that leveled it up again, and then the industry fuel systems related as well went to high pressure systems to help with continue to drive down those emissions requirements. That went another level up, and now we are in the EV and battery explosion. So it's interesting when how, and I'm sure many of our customers experience this as well. You think, gosh, it can't go. There's no place else for it to go, and then it hits another level because something else, another requirement, another change comes along that's requiring our technology.
Yeah, it's pretty interesting. It's twofold. Technology changes. The products are being made to not leak certain materials, and part of those materials are EPA driven. So there's twofold for leak test. It's functionality, and then it's also meeting certain regulations. And the technologies that we use to test all those requirements. Simple pressure decay, vacuum decay, leak testing. Those are pressure technologies for leak and blockage testing. We also utilize mass flow technology. We'll talk about that today for blockage and leak testing, and also functional testing of flow through products. And then trace gas testing as you get into smaller molecular type leaks. We use a trace gas, helium, hydrogen, other gases like argon, CO2, and we'll conduct hard vacuum mass spec leak testing, trace gas accumulation, and then purge containment and sniff testing.
So as customers continue to hop on, I want to encourage you as we move through this training to ask questions. Uh, Chris, if you could monitor those questions and feed those back to us so that we are able to respond to those, that would be great.
Will do. Yep, no
Yeah,
problem.
if you can use using the Q&A, or I'm sorry, it's the chat now to there's a chat button in the bottom of your screen that will allow you to do that.
Yeah. Wow, look at
So
all those instruments.
yeah, yeah. So one of the things that's happened over the years, Russ, when you and I started in leak test, Cincinnati Test Systems had one instrument. It was the I-21,
Mm-hmm.
and it's grown into our breadth of instruments. And the reason for that is twofold. There's a cost implication for entry level type leak testing for instruments like the MH C20 and C28, and their level of simplicity for integrating with PLCs. And then you get into benchtop requirements for the medical industry and laboratory use. And then you get into instrumentation that needs more flexibility, capabilities, and mass flow capabilities, pressure decay, differential pressure decay. So we have instruments that run the gamut of capabilities for leak test and how they function for our customers. And we even get into instrumentation that is multi-channel. The Black Belt Pro is like having 4 instruments in one enclosure. And then the specialty instruments like our 3520 series for filling and testing really large parts are holding flow very, very precisely for mass flow testing. And then the European design instruments for our European customers from Innomatic. The good thing about Cincinnati Test Systems, we are a one-stop shop. So all of our instruments are supplied with leak standards that are built in our ISO 17025 certified laboratory to A2LA accreditation. And those are in both flow and trace gas leak standards. And we also support sealing using the CTS Connects line of pneumatic or manually actuated seal designed components. They make it easy to integrate into a custom or a automated machine, or for simple test station applications that are manually connected and manually actuated. And then a large part of our business is supplying turnkey test systems, from a very simple operator loaded, operator supplied tooling applications to semi-automated systems with light curtains and pneumatic actuations to test systems that are robotically loaded and unloaded in a large assembly or in conjunction with assembly cells. And so those can range price-wise from anywhere from $15,000 to $3 million and support all the technologies that CTS conducts in leak test, for flow testing, trace gas testing, and also end-of-line functional testing. So we can get into the roots of leak testing 101. Russ, if there's anything else you'd like to mention, we can do that.
No, that's it. That is the closure to our advertisement. You know, management requires that if we're going to spend some time and share some wisdom, we have to share what we do prior to doing that. So that is, the commercial is done, and we're going to dig into the nitty gritty of what is leak testing and how it works. And so take it away.
Yes. So the key to leak testing is everything leaks. It's just how much you don't want your product to have material leak into or out of your product as it functions correctly in its use. We have two types of leak paths. One's a thin wall flow path, and that the other is a thicker wall flow path. So as your leak path length changes, the same hole size through a leak path will actually start flowing slower as that leak path grows. And the thing with a longer leak path is it's not just a straight hole through a part. It's a tortuous path. So there are that path will affect the repeatability of that flow and also its flow rate.
Yeah, so we think of castings, right? If we think of aluminum die castings, they've got a tortuous path due to porosity. And then if the thin wall, I always think of a leak standard and the repeatability that would be associated with such a leak.
Yeah, and I'll mention this later. Leak standards are designed to flow with repeatable results, test after test after test. And products that actually leak are not going to repeat as well because of that tortuous path, and the flow path is not a set pattern for airflow through it. And things that will affect your leak rates and um, trying to correlate that flow rate are items like your test pressure, the temp and temperature of fluid if you're trying to keep fluid in or out of your part. The viscosity of that fluid will affect the flow rate, surface tension, and then like we just said, hole size, leak path length, and those leak path characteristics all are going to affect your flow.
So I want to just talk a little bit about correlating leak rates. A lot of our customers want to understand, how does a leak of oil correlate to air? So that's what we're speaking about specifically, trying to take a dissimilar fluid and identify what that correlating leak rate would be with the technology that we're going to apply, whether it's pressure decay or mass flow, which is going to be a flow rate of air or gas as opposed to a liquid. So just to be more specific on exactly what we're trying to correlate, we had a customer do that many years ago, and one of the challenges that you'll find, especially in the automotive industry, is that your parts heat up, and when they heat up, of course, they expand, and that can create some different flow rates due to temperature and expansion as opposed to a standard temperature that you're going to test at room temperature, which is ideal for pressure decay and mass flow. So, okay.
Yep, exactly. So like you're saying, correlating flow rates, the bad news, it's really difficult to precisely um, flow rate because of those characteristics that are changing. The good news is when we're using leak test technologies, we're using air molecules, whether it's pressure technologies or whether it's trace gas technologies, and those gases have much lower viscosity, so they flow more readily through a hole size. And if we start doing some calculations and estimations, you will find that air will flow through a hole size 85 times higher or 85 times more quickly through that hole size than a liquid like water or oils.
Yeah, because when we think of water and oils, they have surface tension, right? And air has a much lower surface tension,
Yep.
and it allows it to flow much easier.
And viscosity, and we can actually do some calculations using this formula and do a correlation of gas flow to liquid flow. And there's a application bulletin on the CTS website that can take you through all the technical details associated with that. And at the end of this calculation, true calculation will give you 120 times to 1, but you need to take into account the leak path length, and that's where it drives it down closer to 80 to 85 times. When we talk about leak testing or when we measure leak testing results, we use uh, pressure as one of the pressure measurements in pascals or psi, megapascals, inches of water. It all depends on the level of pressure that is necessary in the application. And then we also speak in terms of volumetric measurement. That's standard cubic centimeters of airflow or standard liters of airflow, and that's per time. That's per second, per minute, or per hour.
Do we
And that,
talk about it? And I apologize, I
oh,
should
go
know,
for it.
or maybe you're going to talk about it right here, but ACCM versus
Uh,
SCCM, is that
yeah, that's where I was headed with this is
okay?
SCC per minute. SCC per minute means it's standardized to standard atmospheric conditions at sea level, which is 14.696 psia at 20 degrees Celsius. So there's a European standard called normal flow, and the difference between standardized flow and normal flow is they calculate this based on 0 degrees Celsius. And there is a slight flow difference between the two. We can supply a calculation, and it's a calculated difference that's actually on our leak standards spec sheet. And the reason that you standardize or normalize your flow when you're calibrating a system like this is so that you can correlate your testing at atmospheric pressure after you've calibrated. And atmospheric pressure differences are different here in Cincinnati than they are in throughout the places in the Carolinas and throughout the world. So Cincinnati versus Mexico City versus Denver, Colorado. You've now correlated all your calibration back to one condition, that standard atmospheric pressure at sea level at a certain temperature. So you can correlate all your testing results worldwide that way. So I used to talk about bubble conversion to air leak rate, and then I used to talk about water leak rate conversion to air leak rates. And over the past 7, 10 years, a spec has really come evident to a lot of individuals, and that's IP67, IP68, or IP rated measurements. And it's still an attribute test of no water ingress into a part when it's submerged underwater for 30 minutes. And what we've been working with customers is to convert that attribute test to an actual measurement. And 1 meter of water is actually equal to 1.44 psi of water pressure,
Hmm.
which correlates to air pressure. So now we know a measurable test pressure from this spec by saying it's a 1.44 psi test specification with no visible water ingress.
So when you think of a device like that, let's just talk about that for a second, Gordon. You've got a device that it's not like you're going to pressurize that device and measure pressure decay. So how would you realistically test something like that you cannot pressurize?
So you're talking about a sealed part that shouldn't leak water into it. Um,
Yeah, so ingress protection
yeah,
in
yeah.
this case.
So it's kind of interesting. Lots of the IP67 products are things like phones, watches, or enclosures, because that's where this spec comes from. So a sealed enclosure sometimes has a port where our customers will pressurize internally or pull vacuum internally and look for a pressure decay leak. But those that don't, you actually have to put your part in a chamber and do what we call a sealed part leak test using a test chamber with a volume of air, starting volume of pressurized air that equalizes to that chamber. And you test first that the equalization comes to a specific measurement, because a sealed part could have a gross hole in it, and if you just pressurize it with a regulator, you will pressurize the inside of the part and the outside chamber and never test for a leak because the whole thing's holding air pressure.
Oh, so that's why you start with a known volume at a
Yes,
known pressure.
exactly.
Okay.
Yep. So that if your pressure falls below your certain set point, then you know you have a gross leak into the part.
That makes sense.
Yeah, and this type of testing actually started years ago with ECUs, engine control units, that were under hood computers, sealed completely in a die-cast housing, and really has morphed from that to IP67 or IP standards.
I remember, I remember that with a customer up in Grand Rapids, Michigan. Um, Meridian, I want to say Meridian, but they made side markers, and we were, side markers
Hmm.
don't have any holes to leak test, so we put it in a chamber.
Yep, absolutely. Side markers, the LED side markers now are all sealed parts too.
Mm.
Oh, so now part of that correlation is uh, what is water ingress associated with a leak rate? And years of working with our customers, like we said, the flow rate difference of air to water is, well, 80 to 1. And working with certain customers in industry like water faucets or for headlamps, tail lamps, or for radiators, all have identified leak rates for or non-water leak rates, and have been in the range of zero point 0.5 to 10 SCC per minute. The reason for that range is because of what we were saying earlier. Your leak path length is going to affect what your final leak rate is. Short, really short, or really thin parts may have really low leak rates because not only water ingress is required to keep liquid out of it, but also water vapor. So you're testing for water vapor leak rates where condensing water inside a part may cause fogging on a lens, or problems along those lines with really small parts. Where a really large part that may heat up, water vapor may not be as big a problem because it's not going to condense. So leak rate, it then is dependent on the functionality of your risk of failure of what that is. And this is where we start talking about what kind of ranges you may have for your parts with sight windows of 0.5 to 3 cc per minute, or maybe it's a enclosed electronics component that could easily short out. That might be in those ranges. And then thicker walled parts with that don't see altitude changes, like we're talking about water vapor, that would be in the higher leak rates of 3 to 10 cc per minute, and maybe even higher if it's a really thick part with a tortuous path. And as we talk about leak rates and flow rates and test pressures, then we look at what is the relationship of flow to pressure. So if you have a part, well, let's talk about a leak standard, a 20 cc per minute leak standard at 100 psi. So if we test that flow through that same leak standard at 10 cc per minute, or at 10 psi, we will see a 1.4 cc leak rate. And then as we increase test pressure every 10 psi, we see an increase at 50 psi, half the flow of this. At 100, we see a 10 cc, 10.9 cc leak rate. So you can see this mostly linear relationship of flow through the same hole size.
Yeah, and that's one of the common questions that I get and that we get is, what pressure should I test, especially for customers that are new to leak testing and leak testing their product. And our answer to that typically is, well, what is the max pressure that your part will see in operation? So when it's in application, is it going to be 5 psi, 20 psi, 100 psi? What is the max pressure that it's going to see? And then we want to correlate that with an appropriate non-leaking part. So if you want water to not get in or get out, then you'll kind of correlate the leak rate versus the media that you're trying to keep out or keep in.
Yeah, and here's another interesting example. So the water pump and radiator industry right now. Originally, the spec was 4 cc per minute at 16 psi. Well, lots of water coolant systems and powertrain are up around 20 psi now. So it's a 4 cc at 20 psi. Obviously, it's a little, uh, as you're testing at that higher pressure, your risk is a little higher, and they're keeping the same leak rate, allowing for less risk associated with a leak at the higher pressures.
Yeah. So I had another example of that is I had a customer that had not established a leak rate for their products, and they made blood pressure cuffs, and they made child blood pressure cuffs, and they made adult blood pressure cuffs, and kind of everything in between. And they were applying a pressure loss over time, so it could only lose X amount of psi during the test. And what I helped them to understand through the formulas that we've got on our website is that they were testing to one product to a more stringent test than they were testing their other product. And so that's the importance of identifying a flow rate as opposed to using a pressure loss, because the volume of the product is going to have an impact regarding the leak rate. The volume and the pressure are going to have an impact as it relates to the actual leak rate that you're going to be testing for. So that's why flow, and we like to see a flow as the accept reject criteria.
Yep. Yeah, absolutely. And as we're talking about test pressures, so like we mentioned, if you're testing a low pressure and a low leak rate, you may feel, hey, if I increase my test pressure, I can actually increase my reject rate to make it easier to test my part. Well, things to consider when you increase test pressure are the safety related to large surface areas on seals. As that pressure increases, the surface area is going to see more force. You're also going to see thermodynamic issues creep in, and that's associated with compressed gas. When you compress gas, it heats up, and as you increase your pressure, there's a thermal event that you need to stabilize to dissipate that temperature raise immediately after pressurization. Seal creep and deforming your part are two other areas associated with increased pressure. So making sure you've accommodated larger seal cylinders on your test system to accommodate a force that will be applied to that surface area.
One of the things the way I like to explain those thermodynamic issues as it relates to test pressure is we've got about this much volume of air, and then we're going to take that and we're going to open it up. We're going to open the part in our test circuit up to that air. So it's going to expand, and then it's going to collapse
Compress.
again. And that is where those thermodynamic issues come in. Is that we've expanded, now we're contracting, and of course that event, it creates thermal. We can't see it. We can't see those molecules doing this, but they are absolutely interacting with themselves and heating up.
Yep. And parts are going to expand, and we've even seen die castings expand under pressure. So the more pressure inside means it's going to be a little more unstable that you need to stabilize for.
Yeah, in the past we put a dial indicator on a die cast part and put it in without pressurization. Then when you pressurize it, of course, you can see that dial indicator increase, and that is going to change the volume. And so anything that affects the pressure inside of a part is going to affect the repeatability and results of the leak test.
Yep, absolutely. All right. So here's an example also. So we've had lots of customers with really large seal areas say, man, as I pressurize this part, it's really hard to seal. So instead of using test pressure, let's use vacuum. And that will help it create a better seal on the part and make my testing easier. And you absolutely can do that converting pressure specs to vacuum specs. Something to keep in mind though, it's not a direct one-to-one relationship of flow and pressure as it going to vacuum. And that's what this graph shows. Our pressure relationship we talked about earlier is a linear relationship as you increase pressure through the same hole size. So this is a leak standard. Started at 0.2 cc per minute at 1 psi. And you can see at 2 psi it increased by 2 to 0.44. 3 times that is 0.66. 4 times that is 0.8. However, when you pull vacuum on that same flow rate or leak standard, at 1 psi it's not 0.2 anymore, it's 0.15. And as you increase by your psi V through that hole size, you see a 0.32. And what relationship, the relationship in vacuum compared to pressure is there's less air density associated with a part as you increase vacuum on your part. So you're actually pulling less and less air out of it the higher vacuum you pull on your part. So
That makes a lot of sense. So there's less air to actually flow.
exactly. And what we also find as you increase vacuum, getting to around 5 to 8, as maybe as high as 10 psiv, that flow rate actually stabilizes or goes sonic and will remain constant. As much vacuum as you pull on it, you're not going to pull more faster air out of it. It's going to remain that same flow rate. So it doesn't help you to increase vacuum for flow. It only is stressing your part more. So if you're testing for part stress under these vacuum levels, you can increase your vacuum level above 5 or 8 or 10 psiv. If you don't need to do that, then testing around 5 psiv seems to be the right place to stop when you correlate pressure to vacuum.
And if you get to 15 psi
Uh,
we're all in trouble.
yeah, because what did we say earlier? 14.696 psia is absolute vacuum
Just
or
create a
absolute
black
pressure.
hole. A
Yeah,
black
yeah,
hole.
yeah.
15
That's absolute pressure at sea level. So you can never pull more air out of the atmosphere than atmosphere is supplying to you.
unless you are a black hole.
Yeah. All right. So since we're talking physics now, pressure decay technology and mass flow technology uses the ideal gas law, PV equals nRT. So in a normal calculation, you would try and hold all these items constant, and as we conduct testing, holding everything as constant as possible. When we start seeing a leak, that means N is starting to change. So the ideal gas law is converted to what we call the leak rate formula. And the leak rate formula is leak rate, SCC per minute, equals volume. That's volume of the free airspace that you're pressurizing in your part, times delta P, a pressure loss measurement you're going to conduct over your test time, times 60 seconds per minute. That way we're converting this whole equation to standard conditions in minutes. That quantity divided by time, test time in seconds, times 14.7. That's what standardizes it to atmospheric pressure.
So if we didn't multiply that times 14.7, it would be actual.
Yes, exactly. Actual flowing into atmospheric pressure of whatever you're testing in. So that's why it's only actual and it's not, it's hard to correlate those types of measurements without standardizing it. And we've talked a little bit about expanding parts. We've talked a little bit about thermal dynamics of compressed gas. And so there's all these variables that are affecting our leak test measurements. Test pressure affects our measurement. Volume of the part, variances part to part, or variances in your part as it may be changing due to expansion, contraction. That's part elasticity. Internal part movement. Does the part have pistons or diaphragms in it?
We call those virtual leaks.
Yes. And virtual leaks could also be a screw that's screwed into it without thread seal, and threads that can possibly leak into a blind hole with pressure. Clamp and sealing techniques will affect leak testing. Pressure absorption due to porosity, castings all have porosity. Our leak rate will affect leak testing. Cycle time. We'll talk about stabilizing and filling and testing in the pressure decay portion of this discussion. And then our adiabatic temperature effects from compressing gas into a part, or the ambient temperature effects, calibrating in the morning when it's cooler in the plant, testing in the afternoon when that calibration is slightly different than your ambient temperature because of a thermal increase over the afternoon.
Yeah, so I want to, as you look at this list, I always tell customers leak testing is very simple. I mean, obviously, it's complicated. Look at this formula, and there's a lot of things going on, but it's simple if we just remind ourselves that anything that affects the pressure that we are measuring, the pressure in the part, is going to affect, well, I should say the pressure in the test circuit, because oftentimes we forget the line that goes from the instrument to the part, which could go through some valving along the way. All of that, any pressure change in that is going to cause a challenge with the repeatability of our application. So we are measuring pressure change. And when something causes the pressure to change or not be repeatable in the part, it's going to cause our gauge R&R to be poor. And that's physics.
Absolutely. Physics. And that here you are, right? You led right into this, Russ. Leak testing is a measurement of change, and that change associated with a leak. So we want to use a technology that allows us to calibrate the system and remove all those variables from the test so that the only measurement or the only variable we're measuring is that associated with a leak.
Yeah, so we want customers to think of calibration almost as a tearing out. So T-A-R-E. If you've ever had a measurement where you say you're measuring a basket of strawberries, you measure the basket first. So you put it on the scale and you zero the scale. That's called tearing. And then you put the strawberries in, and then you put the strawberry in the basket and you measure the actual weight of the strawberries. Well, leak testing is very similar in that we want to tear out all of those variables and leave ourselves strictly with the measurement of the flow that is coming out of the part.
Exactly. And different technologies will calibrate themselves differently. So pressure decay, mass flow technologies, those are associated with pressure changes. Trace gas testing is associated with measuring molecules coming out of a part. So we'll choose the right technology based on those variables that you cannot control in your application, in your testing application.
Yeah, so some of those are variable leak testing, like pressure decay mass flow is a variable leak test versus tracer gas, which is more of an attribute test.
Measuring that molecular flow. So here we've identified all those conditions again, and this is the order we're going to talk about. Stability of part under test conditions, part variation, test cycle times, test pressure, environmental conditions, device sensitivity, calibration, and sealing and fixture design. So the first one, temperature. Areas that can affect your temperature changes, ambient temperature, HVAC systems. So if your test stand is in your plant underneath a HVAC vent, the as your HVAC system turns on and off, it will affect airflow blowing across your part, depending on its temperature, will affect pressure measurements in your part. if you have operator fans. The key to that is, are the operator fans blowing on just the operators, or are they blowing on the operators and across the test stand? So locating those fans so they don't blow across your test stand is very important. Shipping bay doors is another factor of airflow. So a lot of final assembly leak test is conducted right next to pack out. Right, pack out is right next to shipping department. And what happens in the winter and the summer all day long? Shipping receives and ships product. And as those bay doors open and close, air rushes in, or hot air rushes in, cold air rushes out, you're going to have a temperature change at final assembly test. So watch out for those. And then environmental temperature changes throughout the day. Like we said earlier, calibrating in the morning when the plant's a cool 65 or 70 degrees. By midday, right after lunch, you could come back to the test station and start failing parts due to negative leaks. Well, what's happened in the afternoon is the plant's warmed up to maybe 75, 80 degrees, and you're going to actually test your parts better than they were calibrated in the mornings. And then getting into part-to-part temperature differences. Upstream washers and cooling systems will affect the temperature of a part as it comes into your
Yeah,
testing.
when we say washers, we're talking about part washers, right?
Yes, yes, absolutely. Well, part washers, yeah, cleaning, uh, cutting fluids off your castings, and how that temperature can affect your final part and the leak testing associated with it. And additionally, part temperature can also be, where was that part located prior to this assembly cell? So was it in a warehouse? And the warehouse is at 85. I heard you guys are going to have some sultry 85 degrees. Well, if you bring that into a 70-degree plant, those parts are going to be in a completely different temperature variant than your atmospheric pressure or ambient pressure, and are going to start cooling, which can actually cause false failures or false accepts. The last thing you want to do um, is measure measure for a leak and the part actually has a leak, but it's cooling or warming and doesn't show that it has a leak. And then the other thing is part handling. How long does it take an operator to load a part? Are they standing there holding a part as the as the previous part is being tested? And has their body temperature now converted that part into a warmer part? So that can affect your leak testing, along with your plant air supply temperature. Where is your plant air supply accumulator? Is it outside? Is it inside? How far is it from the test cell? And is your plant air source actually traveling through a ceiling and then down to your test cell? Which your ceiling in the summer could be a different temperature than the ambient temperature around your test cell. So helping control those plant air supply is pretty easy actually. You put an air accumulator at your test station. That way it's a regulated accumulator. It can accumulate air at your cell. It comes to ambient temperature and it doesn't affect your testing at that point.
Yeah. So something that's, oh, what's the next slide? Is it talk about
Oh, yeah, the next slide talks about putting temperature into a part during test. So we could go through that. Uh, it's a video that shows the temperature effect of, and we're going to measure this as a pressure change over time. We have a cylindrical steel part that is teed into a 2 cc per minute leak standard. And I said we're measuring pressure drop over time only, so we're going to see a 0.04 psi drop associated with this 2 cc leak rate. now what I'm going to do is actually put my hand on this stainless steel part just during test. It's all ambient conditions right now, but the minute that I hold on to that part, you see my hand warms it and masks a leak. So this zero point 0.4 psi drop actually turned into a 0 psi drop because my hand warmed that part up and masked that it had a leak in it.
Yeah, and something to emphasize, and I will beat this horse, is that it is pressure change that we are worried about. And so all of these things that we're talking about affect the pressure, because that's what we're measuring with all of these tests is pressure change. Even with mass flow, we're measuring pressure change utilizing flow technology.
Yep, absolutely. So here's another example of how temperature and pressure affect each other, or pressure change affect each other. So we have had a customer came to us and said, we are seeing a lot of variation in our leak testing. We're testing castings that are going through a washer system upstream, and they're coming in and we're seeing this variation, and we asked them, okay, what is the temperature you're testing to? And they said, well, it ranges anywhere from 95 degrees down to around atmosphere 80 degrees. And because of that, we proved to them that that temperature change or temperature difference part to part was affecting their leak testing. So we took a part, heated it up to 85 degrees. It was calibrated at ambient temperatures, and that first time we tested it at 85 degrees, it showed a 2 cc leak rate. So a zero leak part at increased temperature, roughly 10 degrees increase, showed a 2 cc per minute increase. And as we tested that part over and over and over and it cooled, it tested closer to 0 at the end of that test. The other thing that we look for as part to part variation is porosity that absorbs pressure, or flexible parts that expand, contract. And things to accommodate for that is filling your part for a slightly longer time allows you to compress air into porosity, uh, compared to bringing it up to pressure quickly, isolating pressure in the part, and allowing it to stabilize as it absorbs pressure. Forcing air into porosity actually helps to bring it to a more stable condition quickly compared to just going into a stabilized mode. So if you have a set test cycle time and you're trying to test a casting, allowing a little more fill time compared to stabilized time should help you at least get to stable conditions a little more quickly. And then the next thing to understand is the calibration cycle. A calibration cycle is a two-test calibration where you pressurize a part that is non-leaking, measure pressure loss over time for that known non-leaking part, convert that to a 0 leak rate. The second test, you pressurize this part, open a leak standard to it, and then measure pressure loss associated with this leak standard in a non-leaking part. So now you are now you're looking at two measurements, a 0 leak rate and a known flow rate for the 0 leaking part. However, if there's porosity and you didn't allow that porosity to exhaust itself over a good amount of time between the first test and the second test of calibration, you didn't allow all that porosity to come to atmospheric pressure. And it will actually show less of a pressure loss if you didn't allow that to exhaust itself, because you already have air pressure in your part and it's more stable going into the second test.
Yeah, where we see this is some customers they'll test a part and they'll test it again, And of course, this is not, we're not talking calibration here. Let's hit the start button, run the test. It says 5 standard cubic centimeters per minute. And then they immediately hit the start button again, and it reads 4 standard cubic centimeters per minute. And then they hit it again, and it's 3.5 standard cubic centimeters per minute. And then they hit it again, and it's 3.4. And it finally started to normalize after 3 or 4 tests right in a row. And that's because the adiabatic temperature effects are being eliminated, and that masking of, or that porosity, those different variables are all being normalized because we're continuing to hit the start button over and over and over again. So that is something that is common, and customers see that and they say, oh my gosh, my test isn't repeatable. But the reality is that's not the case. It is the fact that you are not testing under the same conditions with which you calibrated.
Yep, absolutely. Other variation that you see, moisture. So standing water on a part will actually cause 2 issues. One, it can mask a leak. So like we said earlier, certain hole sizes have flow rates of air 80 times that of water, and a hole size will actually clog at a certain rate with water. And if you have standing water on your part, you run the risk of clogging a hole or masking a leak. The other thing that happens when you compress gas into a part that has standing water, it atomizes the air. And what happens with humidity, it actually causes lower air density. So lower air density is a measurement of pressure loss that is less compared to higher density air. So now we're getting into some physics associated with air density.
Like, oh my gosh, why is this going to be that complicated for you?
Yeah, and what we suggest to keep water vapor out of your parts as much as possible associated with your plant air source. Use filtered air for your testing. 5 micron and 0.3 micron coalescent filter sets will do that. However, if you have standing water in your part, then you run more risk of this variation associated with water possibly masking a leak or measuring a different pressure drop.
Yeah, when we think about that as well, so if you think about porosity and you think about water masking a leak, what happens is the surface tension of the water, the air is not able to push past that, and it locks up, and so it appears as though it's not a leak, and then the product gets out there in application. Of course, that water that's in there dries up, and the leak path then presents itself.
Yeah, exactly, and that's what I'm showing in this graph is our customer with washers causing heat in their parts was also allowing standing water on their part that was doing 2 things. It was masking leaks and also causing density issues. And you see that where a wet part or a dry part calibrated, tested at 0, and then we sprayed water on it. And what happened? It drove the measured leak rate negative as low as -4 cc per minute. And they're rejecting around 2. So they run the risk of masking leaks all the way down to -4. And as that part was tested and exhausted, it finally started drying out, and finally came back to 0 conditions of flow. So we've talked about variation associated with calibration and relax. Another thing to keep in mind is how you calibrate for leak testing. Back in the day when we started converting customers from dunk testing to air leak testing, they were the attribute test of I dunk this part and it has certain bubbles. I test this part and I see a really low leak rate or a really low pressure drop associated with a good part, but I know my parts leak under bubbles. So I want to correlate this calibration with parts that don't bubble and parts that do bubble. Well, what did we say? Flow rates through parts are not repeatable. And what you want to use as your calibrated part is a non-leaking part with a known flow rate in it, used manufactured as a leak standard that is designed to flow repeatably test after test.
What I always used to say is dunk the part underwater, get a graduated meter, fill the uh, graduated tube up with water, and then put it over the leak and time it. That's what I always used to tell customers. But then you know exactly how
Yeah,
much flow.
exactly. And
That's back in the olden days.
yeah. And interesting enough, that's actual flow because you're flowing into atmospheric pressure at the time you're testing. So another reason to gives you a good start, and then select a leak standard that's standardized so that you can correlate it to other
One of the biggest
tests.
Remember, one of the biggest challenges, of course, is that just because it's leaking out of the part underwater doesn't mean it's going to leak
Right.
out of the part when it's in operational conditions. And that's one of the biggest challenges for our customers to wrap their minds around is I dunk it underwater, there are bubbles coming out, it must be bad. Yeah, it's bad if it's a bicycle tire or a tire that's going on your automobile, but it isn't necessarily bad if it's a peanut butter jar. So,
Yeah. Yeah. What do you want to leak or not leak out of your part? That's what it comes down to. Well, so since we're talking about this, also calibration. There's two different types of calibration. There's a single point calibration and there's a 2-point calibration. A single point calibration is arbitrarily saying zero pressure drop is a zero flow rate. And what did we say earlier? Everything leaks. It's how much you don't want it to leak. So everything's going to show a pressure drop. So if you've set your zero flow rate and then you calibrate to a known flow rate with a known pressure drop on your part, that is your calibrated point. However, as you get further away from that part with a arbitrary zero, your accuracy changes or goes down because you're highly accurate at this known flow rate with all the variables we've talked about associated with your part, but you haven't taken those into account at zero. So to keep that a very accurate measurement as you get closer to zero or further away from your leak rate measurement, you do a 2-point calibration. And this 2-point calibration takes into account all the variables of temperature, atmospheric pressure, part expansion, contraction, porosity, and you tear those out, like we were saying earlier, as your no pressure loss measurement at a zero leak rate, and then calibrate that with a known flow rate, and that gives you a much more linear measurement and accuracy as you get further away from your reject point. Other things that will affect your testing: cycle time, allowing enough time to fill your part to get to a stable pressure, allowing enough time to stabilize your part to then, as it comes out of this thermal event of compressed gas, and then enough test time to see the difference between a known good part and a known reject part. And that also is seen in vacuum. If you don't allow enough time to get down to a certain level in vacuum, then whether it's atmospheric pressure, atmospheric background gases evacuated from your part, or the actual vacuum measurement that you start your testing in, that will also affect your cycle time. Or that's how cycle time affects leak testing. And then device sensitivity. What we suggest is using 100 times more sensitivity for your measurement device compared to your reject requirement. So if you're testing 100 times better pressure drop than your actual reject measurement is, you're going to have enough resolution and sensitivity in your testing device to take your measurements.
Hey,
An
Gordon.
example. If you're using, yes,
Oh, so sorry to interrupt, but we had an
yeah.
excellent question. If you go one slide back, the question is, how do you determine how long fill and stabilize should be for your particular part or application?
How long should fill time be? Well, you can use auto setup in our instruments to help identify that, or you can use the start button, plug in a known good non-leaking part, press start, and then watch how long it takes that part to come up to pressure and then stabilize at test pressure. That you'll see seconds measured on in your instrument, and then also pressure output. So that can give you a rough starting point. The other thing you can do is start doing some calculations based on volume of your part and pressure drop, which we'll talk about here in the pressure decay section.
Yeah. So the first, even prior to connecting up your part to the leak test instrumentation, something you want to make sure you do is put the self-test cap or a stop on the bottom of your instrument and adjust the pressure to the appropriate pressure. One of the big mistakes that I see customers making is they'll put their part on the test fixture and they'll adjust the pressure with the part as part of the test circuit. And that's not the ideal way to adjust the test pressure. You want to make sure that your test pressure is set prior to connecting up and starting to identify what that appropriate fill time is for your application so it reaches that target pressure. So does that answer that question? And then one thing we didn't talk about, and of course we're going to talk about this more in Pressure K, is the stabilization. And
Yes.
how do we determine whether part is stable? So we're going to get into all of that as we continue through here as well.
Yeah, so since we're talking about different technologies and sensitivities, this is a great chart to identify the difference between the sensitivities of each of the technologies and compared to each other. This is an SCC per second measurement because we're comparing trace gas to pressure decay, or I'm sorry, pressure technologies. Mass flow testing sensitivity gets down into the 1 times 10 to the minus 1 cc per second leak rate, and you can correlate that back to multiplying these by 60 to get in the cc per minute range. Differential differential mass flow gets you 1 times 10 to the minus 2 cc per second leak rate range. Pressure decay is about the same. Differential pressure decay gets you down in the 1 times 10 to the minus 3. Dunk testing is actually very sensitive because you're measuring bubbles and looking for bubbles leaking out of a part, and you can see bubbles down in the 2 millimeter range. A champagne bubble, maybe a 1 millimeter bubble. And then accumulation, using trace gas accumulation, gets you in the 1 times 10 to the minus 4, 1 times 10 to the minus 5 cc per second leak rate ranges. Helium is 5 parts per million in our atmosphere, and equivalent to that 1 times 10 to the minus 5 cc per second leak rate range. So to get lower than 5 5 parts per million, you actually then need to start controlling your background, removing background from your testing environment to see more.
Background helium, right? So
Yes.
helium in the background, yeah.
Yep, exactly. So we have 5 parts per million in normal atmospheric pressure. So you either have to change that atmosphere to like a nitrogen purge application or pull vacuum, full vacuum, to start evaluating uh, helium compared to that 5 parts per million in your normal atmospheric background.
A couple of points I want to make about that chart, Gordon, is
Yeah.
the blue on top, and pardon me, I apologize, I'm colorblind, so I'm assuming
Oh,
that so that's blue on top. That is variable. So we want our customers to understand that. And then the green is typically more of an attribute test. And it's not that that green couldn't be a variable test, but the cycle time requirements um, as such, we typically use it as an attribute go no go type of application. So that's one point I wanted to make. And then the second point I wanted to make is that when you look at that blue in particular, you think, gosh, I should be able to test down to 1 times 10 to the minus 3 for differential pressure decay with my application. The challenge is it's application dependent. So part volume, part conditions, environmental conditions, all of those things are going to play a role as to our ability to detect reject criteria down in those low ranges. So that's something to keep in mind that can be a little bit misleading because it doesn't take, we don't see all of that in this chart.
Absolutely. So since we're talking about sensitivity and we talked about variation, what we like to do is work with our customers, understand what their leak rates are, their test pressures, and then help them evaluate all the variables that will affect testing of their parts, and then choose the right technology that's least affected by noise and the variables in their application for the actual testing of their project. And the technologies we choose from, obviously dunk testing, the simplest. The airflow measurement or pressure technologies, we speak in terms of pressure decay, vacuum decay, differential pressure decay, which means either a pressure loss over a set amount of time, a mass flow measurement, and also differential mass flow testing. And then trace gas testing gets into simple handheld sniffing, accumulation, and then hard vacuum mass spec testing.
One of the things I do want to touch on, a funny story about dunk testing that happened many, many years ago, is we had a customer that was testing fuel rails. And the president of our company at the time, Fred McCoy, going around, and we were meeting with the plant manager of this particular fuel rail manufacturing facility, and we made the comment, that 100% inspection, visual inspection, is 70% effective, and that's a proven statistical number that's out there, and the plant manager says, oh yeah, but our operators are so incredibly conscientious. We much better than that. I mean, they do a great job. And so we're like, oh, okay. We go out onto the floor, and the operator is taking the parts, and she's putting them in the dunk stand. And she hits the button. The dunk stand dunks down, jumps under the water. She turns to a table and dries off the parts, and then moves to packaging, and she packages all the parts. And then by the time she turns around, the dunk stand is it's raising back up out of the water. And so she takes them and puts the new ones on and sets the other ones off and dries them off and puts them in the dunnage. And the president of our company walks over to her and says, hey, what are you doing here in this station? And she says, oh, this is where I wash the parts. And of course the plant manager had one of those. So dunk testing is very effective as it relates to detecting leak rates, but it's not very repeatable over the long term, is my point. So
yeah, absolutely. So one of the interesting things about dunk testing is it can be very, very sensitive. And we can convert bubbles to leak rates. 3 millimeter bubble is really hard to measure, but it visually you may be able to understand that. A 1 cc leak rate is converted to 75 3 millimeter bubbles per minute. So that's a real good understanding now. Imagine 75 bubbles, that's almost a bubble every second, or 2 bubbles every second. So a 1 cc leak rate, which is really hard to measure with pressure decay, is a very fair amount of airflow when it's converted to bubbles.
it looks like boiling water almost.
Yes, absolutely.
Right? And that's the thing to think about with it. You're like, oh my gosh, it's leaking. Throw it away, throw it away. But again, it may not leak the media that you're trying to keep in your part.
Exactly. And like we said, non-water leak rates are in the range of 0.5 to 10 cc per minute. So 10 cc per minute is 750 of these bubbles per minute.
That really looks like boiling water.
Yeah. And so we talked about sealed part testing. So there is a difference here. So in this example, we've got compressed gas adding pressure to a part underwater. However, when you start dunk testing sealed parts, and you're looking for bubbles, think about this, is we say a non-water leak rate is in the range of 0.5 to 10 cc per minute. So a part is not, when you've put a part underwater, you've actually added more pressure around it. So the differential is on the outside going in. So air is not just going to normally just flow out of a part. It has to be displaced by water. And the only way to displace water is to actually have a larger leak rate than than an air flow rate not allowing water to flow in, if that makes any sense the way I'm saying it. Uh, water actually has to flow in to displace air. So you have to have a larger leak rate than a non-water leak rate to actually see bubbles of a sealed part dunked underwater. So that's one of the hard things about dunk testing sealed parts.
Yeah, because so what you're saying is in order for it to come out, something has to go in.
Exactly. Yeah.
Mhm.
Or there's got to be a temperature change. So dunk testing sealed parts is really, really tough, and that's why air pressure decay testing is a really, really measurable, repeatable way to do that. So getting into what is pressure decay testing, it's pressurizing a part, isolating pressure inside or on the outside of that part, and then measuring a pressure loss over time associated with a leak rate. And we use the leak rate formula. Leak rate equals volume times delta P times 60 seconds, all divided by test time times 14.7.
That
And this,
calculator is on our website. We can send you a slide rule that has that calculator if you are interested in that. We can
yep,
certainly do that.
absolutely. So um, there's two ways to do a pressure decay measurement. There's using an absolute pressure transducer, or there's using a differential pressure transducer. And we'll get into the differences between these technologies a little later. I just want to present them as two methods for doing pressure decay technology. And then there's mass flow testing. So the difference between pressure decay and mass flow. Mass flow is pressurizing a part and then holding pressure constant on this part. And you will bring it up to test pressure and then go into test. And as this part loses pressure, you actually add more pressure and then measure how much air is flowing into the part as it's held at a constant pressure.
Yeah, so I always articulate that as we measure the amount of flow that it takes to maintain pressure in the part. So same thing you said. I just wanted to say that.
Yes. Yeah, absolutely. Here, the best thing with leak testing here, it's said a couple ways differently. That way it makes sense to everyone. And the sensitivity range of this technology is based on the flow meter range. So a flow meter that is 0.1 to 10 cc per minute has much better resolution at 1 cc per minute than a flow meter that has 0.1 to 100 cc per minute measurement, because those all have error full scale. And your resolution, the smaller your sensor is, the better off you'll be.
And so the challenge that comes in there in choosing which flow meter to use is you say, well, gosh, I'm measuring a 5 SCCM flow rate. I want to use one that's 0 to 10. But the problem is if it leaks 15, you also want to know that it leaked 15, and
Yes.
that's outside the range of the flow meter. So that's some of the give and take that we have to make when deciding which flow meter to use in the application. Something else to keep in mind, and I know we're going to talk about this more later, but it comes to mind now in case anyone has to drop off or anything, is that air pressure regulation coming into a mass flow test is extremely critical, because as you can imagine, if you're measuring the amount of flow that it takes to maintain pressure in the part, if you're upstream pressure is bouncing up and down, then that is going to impact the repeatability of your flow meter because it's going to be pulsing as a result of that pressure change prior to going through the flow meter in the part.
Yeah, absolutely. So as you get into lower leak rates, then we get into trace gas. We can do sniff testing, where you pull vacuum on your part, pull atmospheric pressure out of your part, and then backfill it with your trace gas. The key to sniff testing or testing with trace gas is pulling vacuum, because you want to remove atmospheric pressure from within your leak path so that your trace gas can move through that leak more readily compared to compressing atmospheric pressure into that porosity or into your leak and allowing it to flow until the trace gas gets to the leak portion. Sniff testing is a operator manually moving a wand through a leaking cloud of gas, and that gas is mixing with background atmospheric background. So it's more of an attribute test, like what Russ was saying, compared to a measurable leak rate, because you're measuring it based on atmospheric background. If you want to control that a little better, you can put your part into a chamber and then measure a rate of rise of your trace gas within this fixed contained volume. You can calibrate to that, and it starts converting your attribute test to more of a measurement test. And then to control that more, you actually add nitrogen to your background, removing all the other background elements, so that it gives you even more repeatability and control over the leak rate sensitivity that you're getting to, minus 5 cc per second ranges, even down to -6.
When Gordon says background, he's talking about the environment around the part.
Yes. And then to get into leak rates way below 1 × 10⁻⁵ cc per second leak rates, that's when you pull full vacuum on your part and your chamber, removing all the atmospheric background from the test, and you can measure molecular flow into vacuum with a mass spectrometer. And we only use helium for this. We can do some random gas analyzers, but helium is the most non-reactive, best element to do this with. And the key to all leak testing is to validate your calibration. And to validate a calibration, we suggest having a non-leaking part with a leak standard built into it at 10% or 15% above your reject limit and 10 to 15% below your reject limit, and that will give you a known good part that accepts within a certain range at a certain leak rate, and a reject that actually rejects at a certain measured value as well. So we went through our technology variables. Now we can talk more specifically about pressure decay technology.
Yeah, and I apologize. I'm sure I slowed that down versus your normal
Yeah,
your normal rate as I interjected.
what I'm going to do is actually not discuss every one of the slides that are in this, but at least give everyone a good idea of pressure decay technology and differential pressure decay and how the two differ.
Absolutely.
I'm going to run into a hard stop here at 10, Russ. So we'll work through that, okay?
Okay.
All right. So like we said, pressure decay technology is having a air supply going through a valve manifold and then pressurizing your part. The valve manifold will isolate pressure in the part and allow the system to measure a pressure drop over a certain amount of time. And that pressure drop is calibrated to a leak standard using an absolute pressure transducer, and then we'll talk about what differential pressure decay means along these same lines.
And a known good part.
and a known good part. Yes. So the fill cycle, you're filling through two valves into your part and then isolating that pressure in your part. And we use two valves, one two-way valve and one three-way valve. And the reason for that is you want to isolate pressure in the part and then isolate pressure from moving into the part in case your two-way valve leaks. So that's why this three-way valve is here, helping isolate your pressure and then venting this to atmosphere on the other side of your valve. That way you don't mask a leak. And if that valve actually is leaking, it causes a leak, and you can then troubleshoot to find where the leak is in your system. When we talk about calibration, you heard us say it earlier, you're testing a known non-leaking part for a flow rate associated with a pressure drop a non-flow rate at its internal pressure drops associated with its own pressure absorption and temperature changes. And then comparing that non-leaking measurement to that of a known leak measurement, which occurs in the second calibration cycle. And you've introduced a known leak standard into this non-leaking part and measure that as a master plus leak loss value. And the key to that is having a good cycle time set up so you can see the difference between a known good part and that of a known good part with a known leak in it. So like we said earlier, we're using the ideal gas law, PV equals nRT, converted to the leak rate formula, and in that formula you notice that volume is highly dependent on the pressure drops associated with your parts. So you want to have, if you have different size parts, you will have different pressure drops associated with the same leak rate. The smaller the part, the faster you're going to have a pressure loss associated with the same leak. As a larger part, it will have a slower pressure change associated with that same flow rate. And that's shown here in this quick view. You could have this, if you've got two separate test stations testing the same part and you've changed the test line of one part of one station and you're trying to compare its measurements to that of your other station and it's got a shorter test line, you'll actually have less of a pressure change in that one with the longer test lines in the station. So that's why you need to calibrate these to leak standards so that you take all those volume differences into account and now you have measurable correlated values test station to test station.
And that's also how you understand if you're using pressure loss over time as your reject criteria, the volume is critical. And when you have different volume parts, you essentially are not rejecting to the same criteria.
Exactly. And you could calculate that very easily in this formula by putting in those differences and seeing what amount that really does affect you from a volume standpoint. So we've talked about the ideal gas law and how that's associated with the test. Let's talk about the question that came up earlier, how to determine how long your fill or stabilized time should be. Well, there's steps that you'll take during calibration to validate this. You want to allow enough time to bring your part up to a stable pressure, give it enough time to fill porosity, and then change that over into stabilized time, allowing enough time for pressure to be absorbed into the part and for temperature to stabilize within the part before you go into test. And then test needs to be long enough to see the difference between a known good part and a known bad part. And Russ, you might say, how do I do that? Well, what I want to do is look at my master leak loss and my master no leak loss and see and make sure I've got a difference of at least 0.02 psi value or a 2-to-1 difference between my part with a known leak in it and my part that doesn't have a leak in it.
Yeah. So oftentimes customers say, well, how do I come up with a master part? I always in this the reality is it can be a challenge, especially if you don't have a dunk stand or if there are a lot of leak paths on the part. We calibrate to a part and just run all the other parts. And the one that's most negative is going to be the part that has the least pressure loss. And that's because of this tearing method that we're using. We're using a part to calibrate to, and that establishes zero for all of the other parts. And so if one has a negative flow rate associated with it, that means that it had less pressure loss than the part we calibrated to. Negative leaks is a common conversation that we're having with our customers, and sometimes a tough thing to wrap our mind around.
Yep, absolutely. So here's a real quick visual of a what can happen when you have too short of a stabilized time and too short of a test time. If stabilized time is too short and your part's not stable going into test, this pressure drop, it may be at different values every test. And then if your test time's not long enough, you're not seeing the difference between a known good part and a known bad part. So you want to start expanding those so you're more stable going into test, and you start increasing enough time there in test to start seeing this 0.02 psi difference.
Yeah, so the way I always explain that to customers visually is when we don't have the graphs in front of us is imagine your tolerance window, your accept reject window is here, and then you add more cycle time and you increase your accept reject window by adding the additional cycle time. So now it's much easier to hit this window than it is this window. So your repeatability, your gauge R&R is going to be much improved as a result of expanding that out.
Yep. So we can also do some calculations to make sure that we've got this difference between 0.02 and a 2-to-1 difference between your known good part and known reject part. And using the ideal gas law converted to the leak rate formula, you've got a part that's 10 cc per minute reject rate, 1,000 cc's volume in your part and in test manifold and in your test lines. The part's pressurized to 80 psi, and we know we want to at least have 0.02 psi difference. So we plug that into our formula, conduct our calculation, and we see our test time should be at least 8 seconds to see a 0.02 psi drop in this system. And what we can do is say, okay, let's say my test time's 8 seconds. I want to have at least the same stabilized time for this cycle time as I do test time. And then fill time, what I expect I'll fill my part to 80 psi within these 8 seconds. So you start estimating based on 2.5 to 3 times your test cycle, your calculated test time can give you some averages of how you set your cycle up.
One of the tricky aspects of this, and I know we got to keep trucking through here, but my experience with customers is they say, well, 80 psi doesn't come into play in that formula, Russ. So Gordon, I give to you. I said to you, well, 80 psi isn't a part of that formula. Why not?
Well, so you're pressurizing your part, and your part now is leaking into atmospheric pressure. So it's based on the leak path, not so much the test pressure has been identified as, I'm sorry, test pressure is not part of the ideal gas law. However, it has everything to do with the thermal events of compressed gas on your part and the stabilization. So it's doesn't have attributes of measurement other than variables that are going to affect the test.
Absolutely. Thank you for sharing. And sorry to put you on the spot there. It's
Oh,
just
no
that's,
problem.
that's a common thing because the customers are like, should I test at 50 or 100 or
Well,
200 psi? And the reality is, well, we don't really care. What
yep.
matters is what is the leak rate that you're trying to eliminate at the pressure that your part is going to operate at, or the
Yeah,
max pressure that your part will see in operation.
exactly. Okay, so in a normal calibration, like we've talked about, you have a part, non-leaking part, pressurized, and we do a pressure measurement associated with this non-leaking part during the calibration test 1. And then during calibration test 2, we introduce this known leak standard, 5 cc leak rate, into the test. And in this case, we've measured for a non-leaking part a 0.005 psi drop at 0 cc leak rate, and we've measured a 0.045 psi drop for this 5 cc leak standard built into the test. And you can see in this case we're measuring a 0.04 psi drop associated with this calibration cycle, which is much greater than 0.02 psi. So that tells you you probably have a really good calibration for this project or for this application. What we will do or what the instrument will do is actually conduct a performance factor for you, taking into account what we call a cal ratio formula. That's this formula, master leak loss minus your master no leak loss divided by master leak. And what that does is gives you a ratio of your flow rate associated with a non-flow rate in your part. And in this case, that ratio is 0.89. And you try and at least be better than a 50% cal ratio for testing.
And the best it can ever be is 0.99.
Yes, exactly. The max possible performance factor is going to be 999. Um, and you want to have at least better than 50% performance factor. We have some customers or some applications that are down around 40, and the reason for that is you're taking into account your part, its expansion, contraction, what leak loss you measured in compared to your reject loss, and the performance factor takes all this into account and tells you how good your calibration is for your project.
Yeah, part size is going to definitely impact that, right? So
Yep.
part size versus leak rate. I always explain it as when you're think of a swimming pool. The swimming pool is a large volume of water, and if we're trying to measure a drop of water into that swimming pool, that is going to be less sensitive than if we have a glass of water and we're trying to detect that same drop of water. So the size, the volume is going to significantly impact the repeatability and sensitivity of our application based on the leak rate or reject criteria.
All right. And you can also use the instrumentation auto setup that for setting up a pressure decay test in the C28, I28, and black belt. By just entering these few values in your estimated test cycle time, and the instrument will set that up for you automatically.
Yeah. So what he's saying is it'll determine the appropriate fill, stabilize, and test timers based on a realistic time that you put into the instrumentation. I
Yep.
call it the leak test for dummies button.
That's awesome. And you brought this up earlier, Russ. Negative values aren't necessarily negative. What we're doing is setting a baseline for your zero leak is a certain pressure drop associated with your part. And if your testing actually has less of a pressure drop associated with your tested part compared to your master part, then we identify that as a negative leak rate. However, it just had less of a pressure change than your zero master part did. And that could be due to different porosity, could be due to temperature, and we have some customers that are running into the calibration in the morning at a lower ambient temperature, say like 60 degrees, and then testing in the afternoon at 75 or 80 degrees. As that occurs, your tested parts have less of a pressure drop, meaning the leak rate goes negative, and you can actually set your reject rates to reject in the negative range so that you are aware that this is occurring in your application. We've talked about vacuum. Why test in vacuum? Well, like we said, there is a difference in how parts may seal in vacuum compared to under pressure, and that there is a flow difference. So if you ever are converting your pressure change to a vacuum leak rate, our suggestion is have a leak standard manufactured at your pressure and test specification, and then have a extra cal point for flow at your vacuum pressure that you want to test to, and that will give you the correlated vacuum reject rate for that project. All right. Now we can talk about differential pressure decay, and the difference between differential pressure decay and absolute pressure decay is the transducer you're using to measure pressure change. An absolute pressure decay transducer is pressurized on one side, comparing pressure change in a referenced vacuum, and that's absolute vacuum. When you're using a differential pressure decay transducer, you're actually pressurizing both sides of that transducer to your test pressure, isolating one side and then measuring a pressure loss difference between your test part and this isolated reference volume. And the key to this is your pressure range of the transducer can be reduced compared to the full range of the test pressure that you're measuring in with an absolute transducer. So in that case, what we're saying is we've got our circuit, our source air, our test part, our absolute transducer, we pressurize our test part, and we pressurize our reference volume, bring those up to test pressure, and then isolate those and use a transducer at much less range than our absolute transducer to conduct our measurement. So what we're doing is measuring a difference between the test pressure in our test part and a test pressure in our reference volume.
Assuming that our reference volume does not have any pressure loss, it's going to be a very accurate test for us, right?
Exactly, and that's the key, is having the right controls over your reference volume so that it is a non-leaking volume. And the key to this is some comparisons that we're doing is we've tested the same size part with the same cycle time using the two different technologies and the same leak rate. And the non-leaking part, 0, has a little noise associated with 0. And we have some noise also around our reject rate associated with atmospheric pressure, with the absolute pressure transducer. And then when we conduct that same testing, same volume, same leak rate with a differential pressure decay circuit, we can see less noise on our 0 plane and then way less noise on our reject plane. So what that does is gives us two things: a much more repeatable signal of leak to no leak, and it allows you to possibly reduce your test time because you can resolve that difference sooner in this circuit than you can in this. absolute pressure decay testing is very, very good for certain applications. But if you need to reduce your test cycle time, then you start looking at different technologies, differential pressure decay, to help reduce that cycle time.
Well, that was what I was going to say. Why don't I just use that for every application, Gordon?
You absolutely can. We're helping customers understand that they can and get some ways to use that technology so that it is more of a application for them. However, sometimes there's a cost implication between the two. So then you are looking at your rate and cost implications of what's the best way to conduct my testing.
Yeah, you're saying that was what I was going to ask is what are the drawbacks? Is a differential pressure decay more expensive than a absolute pressure decay?
It, it can be based on the instrumentation you use, but right now we're bringing all our instrument builds together so that there's really no difference. It's more of a, is it the right leak? Is it the right technology for the right application at this point?
Wonderful.
And the difference, like we talk about, is a photo finish of a race. Are you traveling at the same speed as that car to take a picture at the photo finish, or are you sitting on the sideline measuring the speeding car coming by you? That's a visual difference between the two technologies. Just higher resolution with differential pressure decay. And some customers will say, well, why do I need a reference volume the same size as my part? We find 90% of applications don't require a reference volume with the same volume as your test part. It, it gives you, if you cap the system, it gives you very similar repeatability. Certain applications, 2%, are comparing two parts against each other. 8% of those applications have a reference part that's indicative to the same size as their part.
Can you give an example of the
I'm sorry, example of what?
of the 8%?
Yeah, so what we find is in certain applications you'll have a coiled volume of tubing referenced to the same size as your part. That seems to be the right way to use uh, a reference volume compared to a tank. A reference tank absorbs pressure and, well, doesn't absorb pressure. It allows pressure waves to bounce around inside compared to a longer tube that actually absorbs those pressure waves more readily.
What applications would you use that for? Have we found that a reference part is necessary, like a transfer case or a brake?
Engine assembly, transfer case, brake assemblies, a large brake assembly. So maybe larger parts
Okay, large
work
application.
better with reference volumes compared to um, non-larger parts. But even so, it all comes down to leak rate also. Leak rate and
Okay.
test pressure. So each application's a little um, areas where DP does shine when you're doing large part, non-expanding parts, or very small pressure change. That seems to be the best use of differential pressure technology is when you've got cycle time issues and small leak rates. Those, and testing above 30 psi. Those are the times where we really start seeing the applications that shine for differential pressure decay. Basically, it's the um, same graph, same sequence as pressure decay technology. The only difference is a balance when you pressurize both sides of a part and a reference volume. you want to balance the two so that they come to a stable pressure before you isolate them from each other. That's the only difference between the two technologies. All right, so we've got 10 minutes here, Russ, and I think we can talk about mass flow technology.
Good work, Speedy.
All right, so mass flow technology. Like we said earlier, the difference between pressure decay testing and mass flow, you're pressurizing a part and holding pressure constant on the part and then measuring how much air is flowing into the part as you hold it at a constant pressure based on how much air it's losing, and you're conducting that measurement through a flow sensor. This is what a typical mass flow circuit looks like. You have your regulated you have a preliminary regulator set 10 psi above your test pressure. You have a final regulator set at your test pressure, and you're filling a part through isolation valves, bringing it up to test pressure. And once you've brought it up to test pressure, you then need to stabilize pressure in the part for a certain amount of time. And then the fill isolation valves turn on, and you redirect your flow through a flow sensor. And that's when your testing flow measurement occurs. The curve looks like this, where in fill you're flowing a lot of air into your part, and then you're allowing enough time to stabilize pressure so that flow starts to equalize down close to zero, and then you turn on your test time and start measuring actual flow going into the part. And you'll see that oscillate until it gets closer and closer to your stable pressure in your part, and closer and closer to a zero flow. And you can see the two graphs associated with each other. Your fill pressure and then flow rate. And as pressure becomes more and more stable, your flow rate becomes closer and closer to zero. All right. And you're measuring flow rate at the very end of your test time. So this is a instantaneous measurement compared to pressure decay, which is a pressure loss measurement over a set amount of time, where with mass flow testing, you're taking a snapshot measurement and then identifying flow at that time. The key to okay, and you can also calibrate your mass flow system. There's two ways to conduct mass flow testing. That's the normal calibration of your flow sensor, or there's allowing a linear offset. If you calibrate to a part and all the thermal changes or expansion characteristics that occur in your part, you'll offset that by a linear flow measurement to zero. And that's what this graph is showing is depending on when you take your measurement, there may be a flow difference in zero compared to actual flow from thermal events or expansion characteristics of your part, and you can offset those to equal a certain flow measurement in the calibration cycle.
It almost turns it into more of an attribute type test, but
Yes, it sure does. Absolutely does. And that's one of the cautions we always talk to customers about. The key is making sure you've got enough time to get to some stable, repeatable measurement. And then you can offset it if you need to reduce your test time.
yeah.
There's another way to test parts, and that's differential mass flow. This is a technology we've used for testing really large parts quickly. And what that does is fills a reference volume and your test part using a regulated source and bringing your reference volume up to pressure and your test part, and then isolating pressure from being added to the system and only using your reference volume and measuring how much air is flowing into your test part from your pressurized reference volume.
Very similar to differential pressure decay testing.
Yep, yep, where it's a comparison of two measurements. The, the, the key to pressure decay testing and mass flow testing is all those variables that affect pressure decay also affect mass flow testing. The difference that mass flow testing isn't as affected by is the size of the part test to test that you're measuring. If you've at least set up your test cycle time for the largest part variance that you may be testing in your cycles, you don't need to worry so much about part size volume differences during test. So that's one of those things that we'll work with our customers on, is which is a better technology, pressure decay, differential pressure decay, or mass flow, is what type of part variances they're going to see. Is there a volume difference part to part? And if there is, mass flow technology might be better because it's not as influenced by part to part volume differences like pressure decay technology is. And then factors to remember when you're conducting pressure decay testing, factors when you're testing using mass flow technology: use dry, clean air, because your air source is going to be highly effective. Your measurements are highly affected by how dry and clean your air is. And having highly consistent pressure regulation. If your regulated source or upstream source is changing in pressure constantly, it's going to be very hard to regulate that without putting a regulated air accumulator in at your test station. And then also using properly sized flow meters for your flow measurement range. Applications that really benefit from mass flow testing is when you have volume variations greater than 5%. Or if you have a large number of variants and you need to separate those variants into families to accommodate all your different testing setups. And then also if your part has inherent leaks. So if you're testing a part that always leaks at a certain rate, conducting pressure decay technology might be a little harder because you're having to calibrate to this known flow rate that is really large. Using mass flow technology, more of a functional test, usually incorporates itself much better into your application. And then also, mass flow testing works really well in a lab environment because when you're using a mass flow sensor calibrated for its own internal flow measurements, you don't have to have a part to calibrate to. So it works really well in testing random parts and random sizes.
I always tell customers, if you've got applications where you're testing cats and dogs
Yeah,
all day long, then mass flow is the technology for you.
yeah, absolutely. And then having the right range flow meter for all those cats and dogs is also important too. So some of the limitations you have to look out for is testing at less than 0.5 cc per minute. If you're testing in vacuum, which you can do mass flow in vacuum, but as you get greater than 10 psiv, like I said earlier, you get into lower air density and it makes it harder and harder to measure flow because these devices are designed to measure flow. And
Suck the
then
guts out of your flow meter.
yeah. And then also if you're in the low pressure ranges, 0.5 psi and lower, there's not a whole lot of flow associated with that either. And then if you're testing in high pressure, getting above 150 psi tends to be a challenge because there's not that many flow meters on the market that test in that range. And then also if you want to test really quickly, pressure decay technology measures pressure loss more readily than mass flow sensors, because flow sensors are have a response curve and response time necessary for them.
So it's
So
kind of
you
a lag. I always explain it as a lag.
exactly. Yep. Yep. And then again, having repeatability and accuracy is highly dependent on your pressure source, and having that repeatable is going to help your application.
All right.
So we are on the very last slide, and that is a slide that shows a mass flow test, a pressure decay test, and a differential pressure decay test. Well, I'm not going to go into full detail here, but you see the difference in mass flow. You have a fill and a test time and exhaust. So that's where you put your stabilize, is in both fill and test. In a normal pressure decay test, your stabilize is added and your isolate as you've isolated pressure in your part, and then measuring a pressure loss over time. And then in differential pressure decay, you've now turned this into a stabilization between your reference part and your test part, and you have an isolation time, and then you go into test. So that's the end of it, Russ.
Wow, thank you so much, Speedy. I know you have to run. We will stick around for any customers that have questions. We welcome questions. Again, that's how we all learn. So, Gordon, again, thank you so much for joining, and we'll look forward to having you back in April and in May as we continue to go through this series of pressure decay testing for our customers, or training for our customers. I will say some of the bigger challenges that you have to keep in mind when you have leak test applications is that when you have a pressure decay leak test, and you have those negative leak rates, so there's different things that can affect those. So one of the reasons that you could have that is maybe you're testing hot parts. Hot parts are a problem, and that can cause the pressure to change in your application. So if your part is hot, that's going to cause the air to expand, and it's going to appear as though your pressure is increasing in the part. Therefore, the part you're testing is going to have less pressure loss than the part that you calibrated to, and that's going to result in a negative leak. So that's a common problem that you see there. Also, CTS connects. Whenever you have a connector that is connected, those CTS connects are often air activated. So when they are air activated, if there is a problem with the inside cylinder that is causing the actuation, air can leak past or around that cylinder and potentially into the part. So that could cause that pressure to increase in the part as well, creating a negative leak rate situation. So that's a common issue that we need to find. Oftentimes, if you're having a challenge with your application, we always encourage customers to put the self-test cap on the instrument, run a self-test on the instrument, confirm that the instrument is okay. Then you can move on to identify where that leak is for your application, because sometimes the connectors, the line from the test instrument to your part, can become broken, cracked. Right around those connectors those can have issues. The seals where you're sealing the parts, those can have issues as well. So those are some of the things to keep in mind for an upkeep. Your leak standard, when you go to do a calibration and your window is non-existent, that could be because your leak standard has been clogged. And so there's no pressure loss actually escaping through the leak standard, or the valve that's used to open up and allow that leak to flow, maybe it is not functioning properly. That could be an issue there as well. So remember that when the instrumentation exhausts, we talked about exhaust timer, the instrument or the part, that part volume is going to exhaust back through the instrument. And what that can do is, if you are in harsh environments, if you've got coolants, fluids, your air has moisture molecules in there of some sort because of how your environment is, that can get sucked back into the instrument, and that can cause long-term damage to the manifold. So you want to make sure that you are utilizing an external exhaust valve in those particular applications. So those are just some common problems that we have. Another common problem is the pressure regulator on the bottom of the instrument. Operators a lot of times like to mess with those and cause the pressure to be different when you're actually testing the part. So as I mentioned earlier in our conversation, it's important that the regulator is only adjusted when that self-test cap is installed in the bottom of the instrument. That's when we want to adjust that regulator. And then, ideally, I always say I'd like to just use a hammer and knock the regulator or the handle off so that no one could adjust it again, because that adjusting of the regulator is a common problem that customers see or experience. So again, I just wanted to touch on some of the nuances associated with leak testing that cause problems. Just remember, always remember, leak testing is very simple. We are measuring pressure change in the part, and anything that affects the pressure in the part during test is going to affect your test results. It's going to hurt your resolution and therefore make it difficult to achieve the desired gauge R&R. So those are some of the just the basics for troubleshooting. And if you're interested, we can do an entire workshop, 30 minutes or so. It doesn't take too long to talk about all of the common problems, common issues that we see with leak testing and how to help your maintenance people troubleshoot those leak test instruments. So that is it. Please share this information. You can find more information, capexsales.com. We have a YouTube channel. On that YouTube channel, we have lots of videos and examples where we try to share information as much as possible. So the question here from Tiffany. Thank you, Tiffany. She says, is it best to adjust the regulator on the CTS instrument or on the tracer gas test on the CTS instrument? Oh, so you're speaking of a tracer mate type of application. So as long as so in that case, you're going to have, I believe you'll have both of them that will need to be adjusted, one greater than the other. And I apologize. So here you've stumped me at some level, but whatever the last regulator before the pressure, whether the tracer gas is going into the part, that is the regulator that you will want to adjust, is the regulator prior to the whatever the media is that's going into the part. So you want to cap it off and adjust that regulator accordingly. So hopefully that is helpful, but I think that that was what we are touching on there. So in the pressure coming from your tank, you want to reduce that down as well, because those are 2,000 psi or whatever they are. So we want to knock that down and then knock it down further to have a more precise pressure that we're pressurizing the part with. So one of the challenges that can come in, though, as we have more of that regulation, is that we are going to reduce the flow. Therefore, we're not actually able to fill the part as quickly as we would like in some cases, not all cases. So anyway, that's some of the finer nuances. But thanks for the question. Really appreciate it. And then again, pass along, please share this information to your colleagues and anyone that in your location or other facilities that would benefit from this training. And there's a lot of that information, again, is on the CTS website, which is Cincinnati-test.com. And then our website as well has a lot of that content for you, and then our YouTube channel. So thanks so much. Thanks for everybody for attending. Thank you for being customers of Cincinnati Test and CapEx Sales. We don't exist without you. That's why our mission is to continually be pouring into our customers, adding value anywhere that we can. We know that the educated customer is the best customer to have, because you have a better understanding of how to utilize the technologies that we provide and sell. So can't thank you enough for the opportunity to serve you, and look forward to hearing from you soon. Have a great day.